I recently posted a video where I did the Turvy problems 6 and 7 without using the product rule. I eliminated the variables, one of the variables, the radius, ahead of time, and then did the implicit differentiation. Well, for this version of that problem, I'm going to go ahead and run through the product rule. Just in case you don't notice that you can replace the variables, you can still get the same answer. So remember, this is the swimming pool that looks like an inverted cone, Monticello High School swimming pool. Don't really know why they have a pool that's an inverted cone, but let's just draw it. And the height of the container, the pool itself, is 20 meters, and the radius is 5 meters. I can label these numbers right on my picture because those values aren't changing. They do, however, help us with the relationship between the radius and the height. And if you saw the other video, you'll remember that we can use proportions to write down that the radius is always the height divided by 4. We'll just use some similarity to make that judgment. Now, don't forget Mr. Blunden is pouring water in with a hose at a rate of 3 cubic meters per minute. And so this thing is filling up with water, and that water also has the shape of a cone. I'm just going to draw it separately over here so you can see it. The difference is that this water's height and radius are changing, and so is the volume. And so I label those with variables. I don't have to label the 20 and the 5 with variables because those are constant, but in terms of the water inside, the amount of water is changing. Now, they tell us that that hose is pumping out water at 3 cubic feet per minute. That is a rate or derivative of the volume with respect to time. So that's dV over dt, and that equals 3 meters cubed per minute. And we are asked to find, for part 6, how fast the water level is rising when the water level is 2 meters. So for that particular problem, for number 6, I want to know dH over dt when h is 2. We're asking for something else in problem 7. So when I did the problem previously, I wrote out the equation V equals pi over 3 r squared h. And then I used this relationship to replace r with h over 4. And I think that's the best way to attack the problem. It makes things much easier moving forward. But not all students see that right away. And so they may just start doing implicit differentiation. And if you do that, please notice that you have to consider this a product rule. This is a product of pi over 3 r squared times h. So when you do that derivative, you have to follow the product rule. So we'll still have dV over dt, but then in our product rule, we'll have to do uv prime plus vu prime. So just keep in mind that I might be labeling this one u, oops, that's supposed to be a u, and this one v. So if I'm writing out this derivative, that's going to be pi over 3 r squared, the u times the v prime. The derivative of v is just dH dt. Then there's a plus sign, and then we'll have the derivative of u, which will be 2 pi over 3 r dr dt times h. And I'm going to write that as 2 pi over 3 r h dr dt. I just put the derivative out on the right side. And this now is the formula that we have to work with. So here's our issue. Our issue is that in order to solve for dH dt, we're going to need to replace both r and dr dt in this formula. Now, we still are going to have to use our little relationship here between the height and the radius. But this only shows the relationship between r and h. In order to figure out the relationship between dr dt and dH dt, we have to take the derivative of this thing also. So that's going to be dr dt equals 1/4 dH dt. And we'll have to use all that information to solve for dH dt. So check this out. I'm going to start putting some numbers in. For dv dt, I'll put 3. For h down here, I'm going to put 2. Now, for r, remember that r is h over 4, so I'm going to put 2 over 4, which is 1/2. And that means I'll also put the 1/2 in right here for the r squared. And then my only choice with this dr dt is to substitute 1/4 dh dt. Because I'm trying to solve for dh dt, I don't know what it is. So I got to put 1/4 dh dt in there. So my new equation that I'm trying to solve is 3 equals pi over 3 times 1/4, because r squared would be 1/4, times dh dt equals 2 pi over 3 times, not equals, come on, man. I was doing so well, but I had to run into a mistake there. Equals, notice that when I do 1/2 times 2, that just turns into 1. So I'm just, oh God, why did I put equals again? Oh, I should probably backtrack this video up. Let's try this again. That's a plus sign. Come on. I used to be good at this job. Notice that the 1/2 times the 2 makes a 1. So I'm just going to put 2 pi over 3 right here. And then times 1/4 dh dt. Okay, so I'm going to clean this up. This is a pi over 12 dh dt. And then this is going to be a 2 pi over 12 dh dt. That adds up to 3 pi over 12 dh dt. 3 pi over 12 is just pi over 4. So when I simplify this whole side, I get pi over 4 dh dt. And then when you solve, you're still going to get what we got in the other video, which was dh dt equals 12 over pi. So we still get the same value. Took us a lot more work to get there, though. But my dh dt is 12 over pi again, and that's measured in meters per minute. Don't forget that. We got to label our answers. Come on, man. Meters per minute. Okay. Now for part 7, number 7, we still want to find out how fast the radius is changing, which is dr dt. Well, for that, I just go back to this formula right here. I'm going to use a white pencil now to do that. And I'm basically going to do 1/4 times 12 over pi. And I'll do that up here. Dr dt equals 1/4 times 12 over pi. And that's going to be 3 over pi. And that's also in meters per minute. And so we do end up with the same answers. There's no way around using this relationship, r equals h over 4, to solve this problem. And if you don't notice that relationship right away, you'll end up doing your derivative this long way. And then you'll get to here and you'll say, what in the world am I supposed to do with that dr dt? And how am I supposed to deal with these r's that are in my equation? And you'll have to go back to this relationship and do some work. So in the last video, I did that work before I took the derivative. In this video, I did the work after I took the derivative. So hopefully this helps you understand that when you have a product in your function, you have to execute the product rule while you're doing your implicit differentiation. But you can still get to the correct answers. Hang in there. These related rates problems are not easy, especially when there's a container involved that's being filled with some other liquid or some other material. But we'll get used to it. You'll practice more of these, and I think we'll be in good shape. That's it for this video, but if you need me, you know where to find me. Take care.